Okay, thank you. Well, hello everyone. My name is Youngpyo Joo, and I work for SK hynix. I'm responsible for software development of hynix next generation memory solutions. Today, I will talk about our near memory processing solution, which we refer to as CMS, including its architecture and design challenges we have encountered. And lastly, I will share not the programming models, but our concerns about the programming models. So before I begin, I'd like to talk about the motivations behind our research into computational memory. As many of you are aware, there has been a dramatic increase in computing resource demands over the last few decades. In response, we, actually maybe you, have made substantial efforts to enhance system performance. However, these improvements have often come with an increase in power consumption. So therefore, to minimize power consumption, we have explored the concept of near memory processing, NMP in short. So this approach aims to decrease data movement between the CPU and memory by offloading workloads that are inefficient for the CPU. So our focus has been on identifying workloads with low locality, comprised of simple instructions, and those that are memory intensive. Well, in this slide, I illustrated the key difference between computational memory and conventional accelerators, but maybe please let me skip this slide because of time limit. So SK hynix, we introduced our computational memory solution 1.0 at this OCP event last year, first time. This solution offers both CXL-based memory expansion and near memory processing features within a single device. So to demonstrate its practical advantages, we integrated this solution with SK Telecom, a prominent telco company in Korea. Specifically, we integrated it with their in-house database, which is named WritingDB, and it's based on Redis and RocksDB. And our testing was conducted on various Intel Sapphire Rapids platforms. For those interested in more comprehensive details, please visit our booth in the exhibition booth area. Additionally, we have a live demo showcasing vertical integration starting from the user level service application down to the hardware prototype. So this slide provides an overview of the CMS 2.0 architecture. Given its memory nature, the CPU can have direct and unrestricted access via the CXL.mem protocol. In comparison to our 1.0 version, memory space, CMS 2.0 supports host-OS virtual address translation also. So in the earlier version, I mean 1.0, memory space was reserved using DAX, but now with 2.0, now users have the flexibility to dynamically allocate and deallocate memory space in the host OS. While I mentioned the integration with telcos in-house DB, I mean WritingDB, for broader generality, we've integrated it under the Apache Arrow library, which is a widely used columnar in-memory data format and related operations. By supporting data analytics query operations, the performance of a single prototype is comparable to the newest multi-core CPUs, as shown here, with a significant reduction in CPU utilization like this. And by adding a second card, the performance further improves, as shown. And notably, even with the FPGA-based integration, the energy efficiency for these types of operations is better than CPU only. the result comes by running TPC-DS workloads, queries, and we just offer the filter operations for now. Now here are the design challenges we've encountered. I don't want to emphasize the importance of hardware-software co-design and substantial effort involved in achieving seamless vertical integration from top to bottom. Given its dual nature of memory and accelerator, the CMS architecture requires two device drivers, one for the memory path and another for the I/O path, which controls the near memory processing engine. In the subsequent slide, I will elaborate the design challenges related to the coherency, synchronization, and virtual address translation. These aspects are crucial in ensuring its functionality. So maybe all of you already know that why coherency would be the problem. So let's talk about the right point to resolve the coherency problem for now. Since the device operates on CXL Type 3, which does not support hardware-based cache coherency, we should flush data and command from the host cache to the CXL memory. However, an issue arises due to the CPU prefetch mechanism, potentially causing corruption especially in the output result from the near memory processing engine. So to mitigate this problem, we need to execute flush or invalidate operations repeatedly, but these instructions are expensive operations, as you know. So we should explore the optimal point for executing these flush or invalidate operations to minimize the performance impact. And furthermore, we observed that memory allocation consumes a considerable amount of time. So because we need a lot of buffers to use, so to address this problem, we opt for buffer reuse after each initial allocation, optimizing the efficiency of memory allocation and deallocation time. Well, another challenge is synchronization between the CXL.mem and .io channel. These channels operate independently, so there's no ordering constraint between them. Consequently, the following .io command can potentially overtake the preceding .mem transaction. So this scenario results in the near memory processing engine operating with garbage data because the command arrives before the corresponding data. But actually, in our current implementation, we have not encountered this kind of issues because we believe mainly due to at least seconds or the time gap between data loading and the subsequent analytics request. So but by the way, we anticipate that this challenge will be effectively resolved in CXL 3.0 because the new version offers a potential solution through back invalidation operations to the host cache before the near memory processing engine accesses the data. This enhancement will resolve this potential problem. And as I mentioned earlier, we've transitioned from using DAX to supporting host OS virtual address translation to allow their flexibility in memory usage for the applications. To achieve virtual address translation, similar to how the CPU MMU works, some software or hardware or any process should translate the virtual address to physical address. Well, in addressing the host OS virtual address translation, we evaluated two options. First one is software-based solution, which is scatter-gather method, similar to NVMe. This approach involves translating the address on the host side and delivering them as a scatter list to the CMS. This way, the near memory processing engine can easily identify the appropriate physical address based on the scatter list. each software-based, so each software-based translation method. And the second one is hardware-based address translation. It relies on PCI ATS and ATC concepts along with IOTLB. However, we decide not to proceed with this implementation for now, as the software-based first solution showed sufficient performance for our current requirements. But if our next solution or application needs to use pointer type data written in virtual addresses, we should adopt hardware-based translation, I believe, because scatter-gather method doesn't cover the data contents itself. So now I'd like to share our consideration regarding programming models for computational memory. Now we focus to use this solution for data analytics platforms only. So we initially implemented data loading, delete, offloaded functions within the Apache library, as I mentioned. But however, we recognize that manually implementing these functions for every library could potentially limit the widespread adoption of our solution. So to address this concern, we started exploring programming models that would facilitate the easy downloading of user programs. This approach would offer users more flexibility in terms of functions, data format, and applications. The concept illustrated in this image is from the SNIA NVMe computational storage, which supports the download and execution of user programs. Well, this solution could be a good option that can enhance the adaptability and broad applicability of our computational memory solution. But if CMS needs to support only the very simple functions only, like data movement, then downloading program will be too heavy. So in the case, this kind of SDXI style would also could be applicable. I know SNIA began to discuss about to integrate in CXL architecture also. Or unified programming models might be required, as like CUDA in NVIDIA GPU programming. We may need hardcore serious programming models, maybe. This model could domain-specific languages or more general programming models, something like OpenCL or UXL foundations. Of course, this kind of quite heavy programming models assume that we put real programmable compute units like processors onto CMS device. So here's my conclusion of today's presentation. SK hynix introduced CXL CMS 2.0, which shows competitive performance for a certain application domain, I mean data analytics platform, compared to the newest server CPU. But new solution comes, new design challenges, I think. Coherency, synchronization, virtual address translation in this case. So to hide, not only but to hide these hardware-dependent challenges, we are finding proper programming model which gives better usability and flexibility. For now, I think we have two ways. One is big programming model which can cover near memory processing in memory, or computational storage. And the second way would be very simple and minor changes from the current device-oriented implementation. Well, thank you.
So do you have any questions? Okay, so yeah, I have one question. So what is your target application or target system?
Well, for now, as I mentioned, we are focusing on to optimize for the data analytics platform, but nowadays we are looking for other the platform, something related to generative AI.
Okay, so another question is, do you have a plan to integrate your programming model with the OpenCL?
Well, actually not decided yet. We are looking for maybe OpenCL could be one option, but still we are looking for.
Okay, so thank you for your good presentation.